Alright, this video is on understanding graphs of exponential and logarithmic functions. I'm going to try to make this fairly simple for you, but there are 4 things that I do expect you to be able to do with these graphs. Find the x-intercepts, which are also known as zeros, find vertical or horizontal asymptotes, find the domain, and determine end behavior. Remember, end behavior is referencing what happens to the function as x goes to the infinity, which means to the right, or as x goes towards negative infinity, which means as x goes to the left. So let's first take a look at exponential functions, and understanding the basic graph is really key. Here, the basic graph to an exponential function is f of x equals a times b raised to the x. And here is a basic graph of f of x equals 2 to the x. Let's make sure that you completely understand what's happening here. When I plug in 1, 2 to the first is 2. So we notice a point right here at 1, 2. When I plug in 2, 2 squared is 4. That's why we notice a point right here at 2, 4. 2 to the third is 8. That's why we notice a point right here. And then now we notice that a nice smooth curve is made. But let's talk about the negative direction. When I plug in 2 to the negative 1, 2 to the negative 1 does not make you negative, it just makes you small. 2 to the negative 1 is 1 over 2 to the first, which is 1/2, which is why at negative 1 I get a 1/2, a smaller value. And same thing, 2 to the negative 2 is 1 over 4. So it would be 1/4. That's why at negative 2 I get smaller. And hopefully that makes a lot of sense to you. So first off, let's talk about the domain. The domain for one of these functions is negative infinity to infinity. There's never going to be a domain issue when you're working with exponential functions because you can always have any value you want for x, your exponent. However, we are also going to have no zeros. Why do we have no zeros for this function? Because no value will ever make the function 0. If you try to set it equal to 0 and solve, you quickly ask yourself or quickly realize to yourself that there is no x value. If I take 2 raised to that value, it will get me 0. I could use logs if you wanted to. Again, the idea of logs is log base 2 of 0 equals x, and you'll realize that you cannot have zeros in logs. It doesn't make sense. There is no number that you could take 2 and raise it to get 0. So that's why there are no zeros. There is a horizontal asymptote. Because I can't have any zeros, that means there's a horizontal asymptote at y equals 0, meaning that I will never ever dip below into the negatives. Once again, as long as my a value is positive, I'm always going to have values that are above the x-axis. To the left, I will get smaller. To the right, I will get bigger. But I'm never going to dip below 0. Now, in terms of end behavior, just kind of look at the graph. As we go to the right, the graph is going towards infinity. The graph is going all the way up towards infinity. So as I go further and further to the right, this value here, the function itself, continues to go up. However, as I go to the left, the function starts to go towards 0. Now remember, I'm saying it goes towards 0. It never actually gets there, it just goes towards 0. As I go more and more to the left, this value, the actual function, the blue line, will get closer and closer to 0 without ever actually touching it. So we say it approaches 0. All right, let's look at 2 more examples here and try to understand the difference of them. The next one is 3 to the x. So all I did was, instead of a 2, I'm using a 3. How does that make a difference? Well, when I plug in 1, 3 to the first is now 3. When I plug in 2, 3 squared is now 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 3 to the third is 27. That's going to be even higher up here. So we notice that we still have this curve that gets bigger, but it gets bigger faster. Notice that the y-intercept is still 0. Still 1, because when I plug 0 into any exponential function, 3 to the 0 is 1, just like 2 to the 0 is 1. When I start moving to the left, when I plug in 1, I get 1/3, so I get smaller faster. So not only do I get bigger faster on the right-hand side, I get smaller faster on the left-hand side. Plug in 2, I get 1/9. Very, very quickly, I'm starting to get smaller. But my domain is still all real numbers. That doesn't really change. I still have a horizontal asymptote at y equals 0. I still have no zeros. I'm going to use a circle with a line through it to represent that there's none. So all of that stuff is staying the same. As I go to the right, as I go towards positive infinity, my graph is still going up. As I go towards the left, my graph is still going down, approaching 0. However, when I make my a value 1/2, something does change. The entire value, the entire idea of this graph flip-flops. Now, when I plug in 1, for example, 1/2 to the 1 is 1/2. So when I plug in 1, I get a half. When I plug in 2, I get 1/2 squared. 1/2 squared is 1/4. So notice as I go this way, as I go to the right, I get smaller. Plug in 3, I get 1/8. Things get smaller and smaller and smaller. However, when I go to the negative side, watch this, 1/2 to the negative 1, that flips me over. That's 1/2 to the negative 1, which is positive 2. So on the left-hand side, instead of going down like I was over here, now I'm going up. So when I plug in negative 1, I get positive 2 right here. When I plug in negative 2, what happens is I get 1/2 to the negative 2, which is 4, right? Because the negative 2 brings me to the top. So that moves me over here. So notice that my graph now is what we call a decay function instead of a growth function, and I'm doing a very poor job graphing that, but you get the idea that things switch around. However, I still have no zeros. I still have a domain of negative infinity to infinity. The only thing that actually does change is for this graph over here when a is less than 1, as x goes towards infinity, my function actually goes towards 0 now. It's the opposite. As x goes towards negative infinity, which is to the left, my function goes towards positive infinity. So on the left side, the function is going up. Right side, the function is going down towards 0. So that's how that flip-flops and changes things. All right, so if we want to get some basic ideas here of what this graph's going to do, it's pretty simple. If your b value here is greater than 1, then what happens is you're going to cross the x-axis, or the y-axis, excuse me, you're going to cross at a. So whatever your initial value a is. Because remember, b raised to 0 is always going to be 1. So you're always going to start at a. And as you go to the right, you go up. As you go to the left, you approach 0. Very, very simple, easy. If your b value is less than 1, but still greater than 0, because remember our base has to be positive, we're going to get a graph that does the opposite. It's still going to cross the y-axis at whatever your initial a value is, but now on the left-hand side it's going up, and as we go to the right, the graph is going towards 0. So I did a pretty bad job graphing those things, but you get the general idea of what's happening. All right, now let's take a look at one that kind of has a couple things going on in it. Let's just try to understand this function real quick. 2 times 3 to the x minus 4. Easy to understand if you plug in 0. So if you plug in 0, I get 2 times 3 to the 0 minus 4. Walk yourself through this. 3 to the 0 is 0. I'm sorry, I can't believe I said that. 3 to the 0 is 1. 2 times 1 is 2. 2 minus 4 is negative 2. So now I'm going to start down here at negative 2. Let's plug in 1. So I get, come over here, 2 times 3 raised to 1 minus 4. 3 raised to 1 is 3. 2 times 3 is 6. 6 minus 4 is 2. So when I plugged in 1, I got 2. And let's just do one more here. 2 times 3 squared minus 4. 3 squared is 9. 9 times 2 is 18. 18 minus 4 is 14. So at 2, I'm all the way up here somewhere. Okay, now notice that my graph is still going up. Okay, and it's going up pretty quickly actually because it is a base of 3. Base of 3 makes things go up pretty quickly. But understand transformations. We learned about this earlier in the year. A minus 4 on the outside is going to move the entire graph down 4. So we used to have that horizontal asymptote at 0. We now have that horizontal asymptote. And I'm doing a really bad job graphing in here. We now have that horizontal asymptote at negative 4 because it got moved down 4. So our graph is going to look like this. So as I go to the right, it's going up. As I go to the left, it's now going towards negative 4. So I still get that exponential graph that is starting low and then growing, but it's happening all moved down 4. So hopefully that makes a lot of sense to you what that minus 4 does. My domain is still going to be negative infinity to infinity. My, let's see here, my horizontal asymptote is now moved down 4. So it was 0, it's now down 4. So it's at y equals negative 4. Watch out now, we actually do have zeros in a function like this because you could clearly see that it does cross the x-axis. How do you find it? Well, just set your function equal to 0. And if we use our skills that we've learned on solving, this should be pretty simple. Add 4 to both sides. Divide by 2. And now I have to use a logarithm. I'm going to say log base 3 of 2 equals x. So log base 3 of 2 is my x-intercept, or my 0. Now, what is that in terms of a decimal? Well, I can find this real quick. It would just be log 2 on my calculator divided by log 3 on my calculator. I'm just using the change of base rule. It's about 0.63. That is roughly what my value is. So that makes sense. It's actually pretty close to where I drew it there, about 0.63. So don't think that all exponential functions will never be 0. If they get moved around, they very well could be 0. All right, now here's another one. Notice the difference here is I put the minus 4 up inside the function, right? This is up inside the function. It's not down below. It's inside of the exponent. So just like we talked earlier on transformations, when you have your value inside of the function, it's going to move you left or right instead of up or down. So it is going to do the opposite of what you think, like we've talked about before. So this is going to move my graph to the right 4. So remember, normally the graph was our nice exponential function looking like this. It's now going to move to the right 4. So just to make sure that this is easy to understand, always try to think about the center. The center starts typically at 0. Well, now it's going to be a little bit off center. It gets moved around, right? So if I plug in 0, I get 2 times 3 to the negative 4. Okay? Now that is going to be 2 over 3 to the 4th. 2 over 3 to the 4th is going to be a very, very small number, right? So now, because I moved the graph to the right 4, my y-intercept is going to be extremely, extremely low. It's going to be a very, very small number. I'm still going to grow as I go to the right. Still going to grow that way. I'm still going to get smaller as I go to the left, but the whole thing just got moved over 4. Now my end behavior as I go towards the right is still up. My graph is still going up. My end behavior as I go to the left is still getting closer to 0. I still have no x-intercepts because I didn't move it up or down, and my domain is still all numbers. The only idea is that the function got moved over, and you can almost kind of see that in the graph. Okay? So make sure you understand the difference of the transformations in these functions. All right, let's talk about logarithmic functions now. Logarithmic functions are fairly easy to understand, I hope, after we've talked about them. So let's just talk about log x. This is, of course, base 10, so I put a little star there to remind you this is base 10. So the domain, be careful. Remember, when you're working with logs, the inside x value has to be greater than 0. So x has to be greater than 0, which means my domain is parentheses 0 towards infinity. I have to be greater than 0. You cannot have 0, nor can you have negatives inside of logs, which means I have a vertical asymptote at x equals 0. So that means nothing occurs before 0, so there's got to be a vertical asymptote here at x equals 0. Now, how about your zeros? Well, to find a 0, just set your function equal to 0. So 0 equals log of x. Use our definition. That's log 10, base 10. So 10 raised to 0 equals x, which means I have a 0 at 1. So right here is my 0 at 1. So notice as I get bigger, my graph is going up, and it looks like there's going to be a horizontal asymptote there, but there's not. It is going up forever. As I move to the left, well, I'm never allowed to cross over that vertical asymptote, but I do start to decrease here and get closer and closer to that vertical asymptote. Nevertheless, it is important to understand that as x goes towards infinity, the function itself is also going towards infinity. It is going up. It's just going to do it very, 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 very slowly, but it is going up forever. And this is important to understand as well. As x goes towards negative infinity, you might say, well, x can't go towards negative infinity, right? It gets stopped at 0. So don't necessarily think about that meaning as negative infinity. Think about that as x is going towards 0, right? As x goes towards 0, our function is going down towards negative infinity. So as my function moves to the left, it does hit that asymptote and therefore is forced to turn and go down towards negative infinity forever and ever and ever. So hopefully you understand the basics of the domain and the zeros. That's really important for this type of graph. All right, let's take a look at a couple examples here, and let's once again make sure we understand transformations. So remember, the difference here is the plus 3 is on the outside on this bottom problem versus the plus 3 being on the inside. Remember, on the inside, it's going to move you left or right, and if it's a plus sign, it's actually going to go left 3. Keep that in mind. So that means that original log function is going to go left 3, right? So think about that for a second. I originally had a vertical asymptote at 0. Now my vertical asymptote is going to be at negative 3 because it got moved left 3. Let's make sure you understand that in terms of domain. Remember that the inside of a log, which is x plus 3, must be greater than 0, which means x can now be greater than negative 3, which means my domain is going to be negative 3 towards infinity. So now you see why there's a vertical asymptote there. It's also important to make sure you can find zeros. So to find a 0, you're just going to set the function equal to 0. And this is very simple to do. Just use your definition of logs. Base 10 raised to the 0 equals x plus 3. 10 to the 0 is 1. 1 equals x plus 3. That means negative 2 equals your x value. So right here at negative 2 is where I'm going to cross the x-axis. So now my function looks something like this. I still have that idea that the right-hand side of the graph is going up forever, just very, very slowly. And I still have the idea as x goes to the left, I'm going down towards negative infinity, but I am trapped by that vertical asymptote. So that's pretty easy. All right, in this next one, the whole graph does not move left or right, but it's moved up 3, right? So that's not going to affect my vertical asymptote because the inside of the log is what has to be greater than 0. So the plus 3 on the outside doesn't impact my domain at all. My domain is still negative infinity. Sorry. My domain is 0 towards positive infinity. And so I still have that here. The whole graph just got moved up. That is going to change your 0, though. So let's set this equal to 0 and solve. And we're going to quickly see how my 0 changes dramatically. Anyway, now I got to solve this. So I got to isolate the log part. So I'm going to subtract 3 over. So I get negative 3 equals log of x. Now I get 10 raised to negative 3 equals x. 10 raised to negative 3 is 1 over 1,000 equals x. Now that means that my x-intercept is going to be extremely tiny because the whole idea is that the graph got moved up. So the right side is still increasing. The left side is still trapped by that vertical asymptote, but the whole thing moved up. So that x-intercept, let's just kind of go down here real quick, that x-intercept that was at 1, because this whole graph got moved up, now all of a sudden that values down here that get tiny quick is going to move up. And that's why my x-intercept becomes very, very small. Okay, it becomes 1 over 1,000. So it actually doesn't look that much different because it moved up 3, but it did actually change how the graph behaves. So hopefully that is pretty easy to understand, I hope. All right, here's one last question we're going to take a look at. And we're just going to kind of make sure we cover our bases with this. All right, so what's happening here? First off, there's a minus 5 on the inside, so that's going to go to the right 5. Okay? There's a plus 7 on the outside, so the whole graph's going to go up 7. That's our transformation stuff. All right, now, how does that impact all these ever-important values? Well, remember, only the inside has to be greater than 0. So in terms of domain, x minus 5 must be greater than 0, which means x is greater than 5, which means that my domain starts at 5 and goes towards infinity, with a parenthesis, of course. Now, because everything got moved to the right 5, my vertical asymptote is now at x equals 5. The nothing will exist before that, again, because the domain starts at 5. Now, to find zeros, I'm simply going to set my function equal to 0. And we just got done talking about solving equations, so this should be pretty easy. So I'm going to subtract 7. I get negative 7 equals 3 log of x minus 5. I'm going to divide by 3, so I get negative 7/3 equals log of x minus 5. Now I'm going to use my definition. 10 raised to the negative 7/3 equals x minus 5. And that is 1 over 10 to the 7/3. Equals x minus 5, and now I'm going to add 5 to both sides. So I get 1 over 10 to the 7/3 plus 5 equals x. And you could get an approximation of that on your calculator if you just do 1 divided by 10 raised to the 7/3. And that's a very small number, by the way. I mean, think about it. 10 raised to 7/3 is a very, very small number. It's actually 0.0046. Add 5 to that, you get 5.0046. So remember, I have a vertical asymptote at 5, and my x-intercept is going to be very, very, very close to that. It's at 5.0046, which means that my graph intercepts the x-axis right after it. So I just want to make sure that you understand this. So there's my x, or my vertical asymptote, x equals 5, right? And what happens here is the graph is going like this, right? Because that's what log graphs look like. So I have to understand that if I were to go on here and draw in my x and y axis here, right, it's starting really, really close. So here's 5, and it's going to be really, really close to 5. That's because it comes up, and then it crosses almost right near that vertical asymptote. Hopefully you're understanding that. All right, and lastly, as x goes towards infinity, my function is going to go towards infinity as well. That hopefully is easy. Again, nothing's going to stop this right-hand side of the graph from going up, 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 up. It's just going to take its time. And as x goes towards negative infinity, don't necessarily think about negative infinity because you can't go negative infinity, but think about as x goes to the left, my function is going straight down towards negative infinity. Look at this line here as it goes down. It's going down. It's getting stuck with that vertical asymptote, but is continuing to go down. So hopefully that was a quick video. I know I went through a lot right there, but if you remember transformations and you now apply it to our logs and our exponents, it should be very, very easy to understand.